also connects to another intent call by another, and I'll show you that to you guys in a little bit. But one of the things I wanted to show you is with these one-click integrations, we can basically connect it anywhere we want. So, you know, if we go to Facebook Messenger, for example, I can open up the Google Cloud Next test bot, and here I can say my Pixel is not working. And you can see it's exactly the answer that we gave in the bot over there. If I look at the web demo, let's just click through and open it. Imagine this could be your website or your mobile app or wherever, and I can say, you know, I like to buy a few Google Homes. How many would you like to buy? Let's say 6. And then where would you like to ship it to? Let's try this by voice. New York, New York. And so you can see it's adding 6 Google Homes and sending to New York, New York, all in my shopping cart. Now, let me show you how that looks like on the developer side. So if I do the same thing here, and I say, you know, I'd like to buy Chromecasts. Let's even say 5 Chromecasts. You can see it identifies that the intent is commerce. It identifies that it has a product, that it has a quantity, but it has no address. And so it's going to ask me for whatever's missing. Where would you like to ship it to? And now I can say 5 5th Street, New York, New York. And now notice how it created a shopping cart context. I can go to buy another, which is only activated with a shopping cart context. And let's say I say another one, please. What it did here is it added one more to my shopping cart. And now instead of 5, I have 6. If I do it again, you can see it'll say I have 7. So this is a 3-4 lines of code program that I wrote in Cloud Functions that's connected here with a webhook. And so we have this whole store conversational AI bot that was really created in roughly 15-20 minutes on stage, plus those few lines of code. Pretty easy to do. And you can now deploy it in all these channels, and it works across everything that you'd like. If you go to these one-click integrations, you can connect it to any platform that you want. There's a few other things here that I'll just point out. We don't really have enough time to kind of go through them in detail, but we can make this a multilingual agent. So right now it's in English, but if we want, we can add a second language, and it will work in more than one language. There's a training tab here, so we can use some of the logs of conversations that have happened and tag things that we think it handled well or things that it didn't handle well, and add that to the training data that goes into the machine learning model. We can look at sort of some basic analytics integrated into Dialogflow, or use Chatbase that has more advanced analytics. And for fulfillment, we can either connect to a webhook, which is what I did, or if you look here in the bottom, there's actually a built-in code editor that you could use to build a full application right within Dialogflow. That's all we have time today for Dialogflow. But let's go back to the presentation and talk about speech. So Cloud Speech API is our commercial offering for speech recognition. It's available in over 110 languages. You know, it works in real-time streaming and in batch, and it works in noisy environments, and it offers phrase hints. But really, the interesting story about speech, it's you know, we built speech recognition internally at Google more than a decade ago, and it was never meant to be a commercial service. We kind of built it for our own internal purposes at Google. We've had to build it to work really well. And so it's built on a scale where it serves over 2 billion of our Android customers and hundreds of millions of iOS users. And the service is built to work in all of these different places that our users use it. So whether that's a person talking on a busy street in India with buses passing by, or another person asking their phone in Times Square in New York how to get to Union Square, it's really built to work in all those places. And now, starting from earlier this year that it was declared GA, we're now making this available to anyone through the cloud. So we're democratizing this technology, basically. So any startup, any enterprise, any student now has access to the same quality of speech recognition that Google's engineers do, which is very exciting. The technology has existed for a while, but what's interesting is now we're at an inflection point, because now it's actually much better than it ever was, and it opens up much more use cases that previously weren't available. So, there's two main sets of use cases. One which is around human-computer interaction, so things like mobile apps, web apps, IoT, phone-directed apps. All of these things, speech can now be used for, because it's good, and it works really well with Dialogflow that you saw earlier, because you can now create voice-powered apps that work across all of these devices. You saw earlier in the demo how that could work. Another set of use cases is for speech analytics, where you want to look at human-to-human conversation and get some insights from that. So that could be call center analytics, it could be video analytics, it could be meetings analytics. There's three ways that you can use speech. Streaming, the regular recognize or long-running recognize. So we support all of them. Each one has its advantages. And we support a wide variety of standards, languages and formats. Especially if you look on the left, it's pretty wide language support, and we're trying to make it easy to use, wherever you're coming from. Best practices for human-computer interaction is we recommend using streaming, because latency is really important for that use case. So it's worth the effort. Uncompressed audio or lossless compression is really preferred, and 16 kilohertz sampling rate or above for that use case. And phrase-ins really helps, because you have an idea of what the user might want to say. For speech analytics, we recommend using long-running recognize, because it's better suited for long files. Splitting speakers into channels is something that could really help. So if you're analyzing a phone call and there's two speakers, one on each channel, sending a stereo file that has both of those would be something that would be beneficial, versus creating a mono channel that has both of those speakers. That's a little bit harder to recognize. One other tool we have is DLP. So if you recognize speech that has PII in it, DLP can help you clean up that PII, and you should go. You should just look at our docs, learn more about it. It's a pretty cool product. So let me just show you a quick speech demo, so you have a sense of how speech works. So I'm throwing a big party this weekend, so I'm going to go to the supermarket, and I'm going to go buy some meat, and then I'm going to meet some friends. So I think that got 100% accuracy. It's not always 100% accurate, but when you use kind of high fidelity recording, it works really well. The other thing you guys may have noticed is that as I was talking, it was appearing on screen almost at the same time. It's really fast, which is really great for a lot of applications. The other thing you may have noticed is I was talking slow and fast in different sections of the utterance, and I was saying ums, it kind of cleans it up, and you can see really what the user intended to say. And last thing, I said the word meat twice, and you can see how it differentiates between meat and meat. The other cool thing is that it's really good at recognizing named entities. So to see that, I'm going to show you guys another demo, which is our it combines our speech recognition API with our natural language API. Our Cloud Natural Language API helps you identify sentiment and also recognize entities. So let's see how that looks like. I really like the Beatles. I love New York. And so you can see it identifies sentiment in these utterances. You can also see the speech recognition actually capitalized these terms because it knows they're named entities. And then the natural language API helped us identify them, extract the entity. And you can see these cards that are coming in from Wikipedia or from the knowledge graph. So that's a combination of speech API and natural language API. To learn more about Dialogflow, you can go to dialogflow.com or to cloud.google.com/dialogflow. To learn more about speech, go to cloud.google.com/speech. To learn more about natural language API, go to cloud.google.com/NL. Thank you for spending this time here with me. I hope you enjoyed it. Please don't go anywhere. If you have any questions, there's Googlers here to help you. Otherwise, just stay tuned, and there's a bunch more sessions here for Cloud on Air. We're looking forward to staying with you here. Thanks.
Hi, and welcome back. Hopefully you enjoyed that session from Dan talking about Dialogflow and how you can build chatbots easily.
Yes, and I agree. I think Dan spoke a lot about Dialogflow, which is our product which was called API.ai earlier, and now it has been set out for the enterprise version, which is called Dialogflow. So it's really interesting with all the use cases that he mentioned. And the next session we're going to have in the AI track is the machine learning at scale, which is about running TensorFlow in the cloud.
Yeah, definitely a really interesting session. And also coming back, who have just joined us, is the industry solutions track. So welcome back. So they just finished the financial services track, which is a really interesting track, and they're about to talk about retail customers in the next track for industry solutions. And then finally, our big data track just came back as well.
So I think the big data track just ended with simplifying ETL for stream analytics solution. And it was an amazing session by Sergey. And now we're going to move ahead with the next track in big data, which is about fast tracking Apache Spark and Apache Hadoop with Google Cloud Data Proc. And I think this is going to be a really interesting session to watch out for. And what do you say, Jay?
Yeah, so I think, with Spark and Hadoop and actually TensorFlow, we're really talking about a lot of the open source technologies that we have available that you can use on Google Cloud. A lot of these things you can run on premise on your own machines, and you can run on Google Cloud. And I think it's important for organizations to make sure that they can move their workloads between premises and clouds, and whenever they're using Google, hopefully it's because we're giving them the best price per performance, and we're taking away a lot of those headaches that they would normally experience when they manage their own clusters.
I agree. And I think it's all about open source at Google. And quickly, I think before all of you get started with your next tracks, I think a quick reminder of the Q button that we have on your left-hand side, which is to ask questions real time throughout the session, throughout any of the tracks that you're attending. And please select your track out of the 3, whichever one you want to attend.
Great.
We'll see you soon.
Welcome back to our global online conference, Cloud on Air, the journey from big data to AI. My name is Yufeng Guo, and today I'm going to be talking to you about machine learning at scale. Before we dive into things, I want to just make sure we're all on the same page about what is machine learning. For me, I've boiled it down to just a few words. Machine learning is using many examples to answer questions. We can take this definition and split it into its kind of two main parts, using many examples and answering questions. Those two correspond to training and prediction. These two parts are equally important, and they can be both done in the cloud or on your local machine or your local server. The training part, of course, is important and focused on a lot because it is what determines the quality of those answers. But I want to emphasize that the predicting or the answering of questions is equally important, because if you have the best model in the world, but you can't serve up your predictions to your users in a scalable manner, then what good is your model? So we'll take a look at both sides today, both the training and the prediction of machine learning. So stepping back, I want to just introduce, for those of you who are not familiar with it, TensorFlow. TensorFlow is Google's machine learning library, and it was open sourced in November of 2015. It's a fast and flexible library that is good for both research and prototyping, as well as being deployed to production. At its core, it is built on a distributed runtime and is made to scale. TensorFlow means the flowing of tensors. Tensors are just multi-dimensional arrays, and to flow them, it's just referring to having them flow through a graph of operations. So in this simple example of a graph, it's taking the 2 and the 3, and it flows through an addition operation to yield a 5. So at its core, these are the kinds of things you would see happening when running a TensorFlow program. But we'll operate at a much higher level of abstraction. TensorFlow supports many platforms. It supports the ones you'd expect, like CPUs and GPUs, but it also runs on mobile and IoT. So for those of you who like to tinker or build apps, there's something here for you with TensorFlow as well. As I mentioned, TensorFlow runs on a distributed execution engine. And the front end of TensorFlow is wrapped with Python and a few other libraries and languages as well, but we'll focus on the Python option today. On top of this Python front end is a number of layers of more Python. First, we have the layers library, then the estimator library to help you build those models and run the evaluation loop for you. And what we'll focus on at the very top level are what we call canned estimators. They're models in a box, and they take care of just about everything, but still leave you the flexibility to configure the model to your liking. And so that's kind of the benefit here, is you trade off a little bit of customization while gaining a lot in terms of having a system that can be distributed and scale for you very nicely. So a quick example of what this looks like, let's focus in on the middle here, this is making a deep neural network classifier. And you can see that we only call a few options here to configure a model rather than building one from scratch. And for those of you who are familiar with machine learning and say, well, I want to configure everything, we got a lot of options for you to play with here as well. So it takes a while before you need to actually go down a level and build up a custom model truly from scratch. So that's enough code for the time being. Let's back up, and I want to tell you guys a little story. Let's say, a little thought experiment, we're going to make a new startup, right? We're going to make the hot new app, and it's going to predict what our users want to eat. Totally original idea, I know. And let's say you think about a use case, right? Someone says they want fried chicken, and maybe they get chicken and waffles. Okay. And so with that, you say, all right, I'm just going to launch and iterate. I'm going to do naive text matching and just say the user said fried chicken. I'm going to look it up in my menu and see which ones match with the words fried chicken. So the user, you launch it, the user says fried chicken, and they get chicken fried rice. Not exactly what they were hoping for when they said fried chicken. So how can we fix this? Well, you see the feedback in your reviews on the App Store, and you'd say, it's OK. I'm going to reach into my machine learning toolbox and pull out linear regression. We're going to use basically fit, align, and memorize our users' preferences. So we train a linear TensorFlow model, deploy that, and your app starts getting traction. It's doing well. And the problem, though, is that now we're seeing a different kind of review. People are saying they're getting bored. Every time they ask for fried chicken, they get chicken and waffles. Every single time. And so your users are picky. Okay, that's understandable. And so you say, it's okay. I'm going to reach into my deep learning toolbox again and pull out deep neural networks. This will allow us to have generalized recommendations rather than memorizing the specific mapping from one request to its matching food item. One of the reasons why this works so well is that it leverages what are called embedding spaces. An embedding space is simply a way to represent our data so that they are kind of spatially more accurate, so that when things are farther apart, they're different, and things that are similar are more closer together. So say, for example, you have all of the fruits are clustered in one area of your space, and things like your grains are over here, your vegetables are closer together, and your desserts are somewhere else. And so this allows you to, when someone requests an item, like fried chicken, they will get something in that general vicinity. Maybe instead of chicken and waffles, they get chicken and pancakes or something. And so with this, your app starts doing quite well. It's doing well, but no good deed goes unpunished. You worked so hard, you implemented this deep neural network, but sometimes your users ask for a very specific thing. They're still picky. And so then they get something similar to that very specific thing, and they're not happy about that, right? For example, let's say the user asks for a iced decaf latte with non-fat milk, but they get a hot latte with whole milk. Not exactly right. So there are certain things that users really want you to give them what they want, give the people what they want, right? And certain things where they would just want general options, like when they ask for Italian food. So how do we balance these two requests? Well, luckily, Google Research published a paper a little while ago called Wide and Deep, which takes these two models and combines them into one. You have the deep side and the wide side, all as one model giving predictions. So they called it Wide and Deep. The wide side gives memorization, and the deep side gives generalization. And together, they work better than either one was able to work alone. The way you can conceptualize this is that the deep side does pretty well at generalization and covers most use cases. And the wide side takes care of memorizing the exceptions, so that this way the two of them kind of cover for each other's weaknesses. So that's enough for a story. Hopefully I've made you not too hungry to stick around. So we're going to go and take a look at an example. We're going to use a just as exciting data set as food. It's going to be census data. This data was created from the 1994 US Census and prepared by Barry Becker. It's a very classic machine learning data set, and it's a very straightforward problem. Well, to the extent that machine learning can be straightforward. And the task is to predict whether an individual household has an annual income of above or below $50,000. So 0 for below and 1 for above. So very kind of straightforward. And what we're going to do is take this data set and use it as a just example to run through the workflow. So you can then plug in your data set to this same model. We're going to use the wide and deep model, and we're going to run it against our census data. So before we do that, let's take a look at what this data set actually looks like, right? We have a bunch of columns, things you'd expect: age, education, occupation, the number of hours they've worked per week. And what I want to point out is that some of these columns are continuous, meaning that they're just numerical, and some of them are categorical, so that they have specific values that are possible for each one. Now, the final column, of course, is income bracket, which is just a string of greater than 50K or less than or equal to 50K. So we'll process that into a 0 or 1 shortly. So with the wide and deep model, what will happen is we'll plug in the categorical columns or the sparse columns into the wide side, while while the continuous values go into the deep side. And there's some overlap, and we'll do some feature engineering to kind of allow both sides to see quite a number of options here. And that's where it gets really interesting. So let's go to the code and see what it's all about. So here we are in my Jupyter notebook. And the first thing, of course, we'll do is import TensorFlow as TF. So later when we see TF, that's our TensorFlow module. And we'll run this. We'll have a couple of columns, just all the names of different columns that we'll use to load in our data. Our data happens to sit as a CSV. And so the first thing I want to do is load it in with pandas. Pandas is a really nice way to play around with our data and test out what it looks like, run some basic statistics against it, and the like. So we'll use .head to see just a couple of sample rows. We see here that the different columns are, some of them are strings, some of them are numbers. It's a good way to just have a glance at the data, make sure it's well formed. Next, we'll run .describe. .describe has a number of statistics about the numerical columns, while if you pass in include NP object, you can get the categorical ones out as well. So the numerical ones, you can get some interesting statistics and see that the max hours per week was 99. So in 1994, nobody worked over 99 hours per week, and nobody worked less than 1. Furthermore, we see that nobody exceeded the age of 90 in this data set, which is also kind of some funny things there. And then on the other side, we'll see that the categorical columns, some of them have a lot of options. Like native country, there's 41 different values, while some of them have much fewer options. Like marital status has 7, 6 values for relationship, and so on. So let's make sure we run these cells, and then let's move on now to the actual TensorFlow. So the first thing we'll do is talk about input functions. Input functions are TensorFlow's way of wrangling our data from their file into our model for training and for prediction. So what we'll use is the pandas input function. This is a utility built into TensorFlow that lets you use pandas as a way to pass in your data directly, so you don't have to wrangle with shuffling and batching by yourself. And so this just serves as kind of a convenience function. You'll also notice that we used a .apply on our data frame to change our label column from greater than or less than 50K to zeros and ones by just casting the true-false result as an integer. So let's move on from here. This function will give us our input functions as needed and create our feature columns. Feature columns are really the interesting thing here that is worth looking at, because with feature columns you can specify the way that the data comes in and the way it looks. So let's take a look at this one, right? We have a categorical column with vocabulary list where you supply all the possible values of a given column based on your data set, and there's an alternative, of course, of using categorical column with hash bucket. So if you don't want to type out all the possible values, there's an option for you there too. So if you have like a data set with lots and lots of columns, just way more columns than you want to configure, you could do a for loop and just do categorical column with hash bucket and be all set. So we'll run that, and then we'll move on to continuous columns. Continuous columns are a bit simpler. Just call numeric column and give it a name. You'll notice that so far we have not actually connected our data to these feature columns, right? We didn't put our data, have an input function, and then put our feature columns into the input function. These feature columns live kind of separately, and what will happen is we'll connect that to the model, and the input data will pull in the data, and then these two will come together when it's time to train. So make sure we run that, and then what we'll do is some transformations. The transformations are interesting because you can take our feature columns, let's say age, which was continuous, and turn it into a categorical one, age buckets. This might be useful in this case because you say, well, I don't want the data to be all continuous, one value, one value, but rather I want them to be grouped into buckets. So this TensorFlow lets you do that with one line of code. Furthermore, you can do feature crosses, which allow you to combine features together so you can get build certain relationships that you know or suspect exist. And you can actually take that age buckets column that we just created and cross them with other categorical columns together. We can take a continuous column, bucketize it, and then cross it with other columns, which is fantastic. So we'll run that. And now the next thing we'll do is pretty straightforward. We'll just group them together. We'll take the wide columns, all our categorical columns and cross columns, and put them into an array. We'll call it wide columns. And we'll take the other remaining columns, all our deep columns, along with all of the other wide columns and put them into embeddings to group them as deep columns. So this is where I was saying that the deep columns can capture quite a bit of information. We can take our education and native country values and put them into an embedding column. For the other ones, there were fewer unique values, so we'll put them into what's known as an indicator column, which is a less complex representation, which is suitable for a data set that had fewer, for those columns that had fewer possible values, like marital status or a relationship and the like. So we'll run this, and now comes the interesting part where we get to create our model. So creating our model is super simple. This is going to look a little bit familiar. We saw an example with DNN classifier in the slides earlier. The wide and deep model is implemented as part of TensorFlow, and it's called a DNN linear combined classifier. Take a breath. Yeah, it's a little bit long, but it gets the job done, and it's a really good starting point, I've found, for this type of data. You have structured data, you want to do some classification or even regression with it, which is the same name, but replace classifier with regressor. And you can just throw it at this model, and it'll just give you something reasonable to start with. So we have a couple arguments here. We pass in a directory to store TensorFlow's training artifacts. We'll pass in our wide columns. We'll pass in our deep columns. And importantly, we'll pass in our deep hidden units. So the hidden units is kind of our deep neural network's structure. So if we wanted a network with 4 layers and have those 4 layers be 100, 70, 50, and 25 neurons each, you could just pass in this array. But if you decided, I really want to have just 3 layers, simply delete those values, and there you have it. So it's really flexible and allows you to test a lot of different architectures. So we'll run this and create our model. And next we get to the fun part, right? We get to train our model. And training our model is super straightforward with TensorFlow. When we created our model earlier, we saved it to a variable m. And so what we're going to do is we're going to say m.train and pass in our input function with our file from the training, the CSV. And so that'll load into pandas, generate the pandas input function, return that, and it gets passed in here. We say just do 1,000 training steps just for the sake of this demo, and we can see that just as a first pass where we really didn't have to configure that much. Right? We just picked some values, and we can see that we can do the training and have a result very quickly with just a few lines of code. And now what we want to do next is run our evaluation. So while we're waiting for this to happen, let's talk a little bit about kind of the arguments that I'm passing into the input function. In particular, with the evaluate input function, what you'll notice is that not only am I passing in the file, but also a couple of arguments around APAC and shuffle. So with evaluation, you want to go through just one pass through the data. So that's what APAC is, how many times we run through the whole data set. And then shuffle is false here because we need to go through the whole thing anyway. There's no need to shuffle everything. So our evaluation has completed now, and we can see that we achieved an accuracy of 82.8%. Not too bad. Not amazing, but not too bad for a first pass where we basically arbitrarily chose some arguments for our model. Definitely a good starting point. So let's see how we can now make a prediction using that same trained model. What I've done is I've loaded in a couple of rows from our evaluation data set, and we can just take these 5 rows, which we expect to be over here, if we look at this, less than, so 0, 0, 1, 0, 0, to come back for these 5 values. So we'll use, you guessed it, another input function to call prediction. And when we do that, what we'll do is we'll pass in the data frame that we created with those 5 values and batch it up just one at a time through the whole data set and not shuffle it. So it's a similar thing to evaluation. And we can see that the answers are indeed 0, 0, 1, 0, 0, as we expect. Now, we train a model, you'd probably go back and fix a bunch of things and make your model better. But once we are happy with the model, we're ready to move on to the other side of machine learning, the prediction. And what we want to do there is export a trained model for doing our predictions. So this exported model is different from what we use in training in that all the loops and feedback that it is built into the TensorFlow graph, we don't need it for prediction. We just want to fire off predictions as quick as possible. So just send that out, and what that means is you want to export a model that is stripped of all those things so it can run fast and lean. So here we're going to run this, and we're going to call model.exportSavedModel. This takes care of doing all of that for us. And you'll notice that there's a couple other things going on here, notably that there's a serving function. So the serving input function is the same kind of idea as the other input functions we saw, but this is specifically for serving predictions. And so what happens now is it writes a savedModel.pb file to a directory of your choice. And now we can move on to talking about how we load in predictions. So how do we scale our predictions, right? We have scales and maybe scales, but we want to really scale, right, to the cloud. And the way we'll do that is we'll take our exported model and put it into Cloud Machine Learning Engine. Cloud Machine Learning Engine allows you to very easily have a scalable prediction service that you've custom trained, and it has great integration with all the other services within Google Cloud. And so not only can you do training with it, but you can also do this prediction. So we'll focus on the prediction today, and other sessions throughout this live on-air event will also talk about the training side of CloudML. So how do we create a model? Well, we did a lot of model creating just now, right? But now how do we create it in the cloud? Simply put, you can do it by just hitting Create Model on the UI and giving it a name. And voila, we've created a model. But all we've done is give it a name, right? So when you export these saved models, right, you're really giving versions of your model. And each time you create a new version, maybe you've updated it and made it better, you can export that and create a new version. So the model is really just a wrapper around all of your different versions. Depending on the maturity of a given version, you might select that one versus a different one. So let's take a look at what it takes to create a version. You click Create Version and give it a name. But this time we're also going to pass in a location in cloud storage for it to pull the model from. So you can see here I've uploaded savedModel.pb and a folder called variables, they live side by side, into cloud storage. And we can use that cloud storage location and just paste it into here to create a new version of our model. So in this case, just v1. But if you had more, you would create another version. You could call it v2. You can give it whatever you want to call it. And you can now, once you have this, you have a auto-scaling prediction service. This means that when you have more demand, it will scale up for you. And when you have less demand, it will scale down all the way to 0. So what's neat about this is that as data scientists, we want to play with our data. We want to train models. We want to tune parameters. We don't want to be bogged down in doing ops and working on how we can scale our system, right? Once we have it trained, we just want to get it out the door so we can continue working on this. So it allows you to do that. And you can do everything we saw on the command line as well, here, as we've shown here. And there's an API, so if you want to script it out and automate it. Now, once you have a model in place, you might want to do some predictions, right? So what does that look like? Well, here I have an example with just 2 JSON examples. We'll load that into a file called census.json and call the prediction service. The Google Cloud G-Cloud ML engine has a predict operation which will kind of wrap up the API call for us, but it's just a REST API. And that means you can call it from virtually any library, any language, and as well as calling it from a mobile device and IoT. And we see here in the response that we get the classes on the left and as well as the probabilities of each of the 2 different values. And if you want to do a batch prediction, you can do that as well. It looks very similar. You can pass in this file and it runs it as a job and outputs each prediction as a separate file. And so you can see the logs as well. When you run the job, you can view logs to see all the things. So when you're running predictions, it will actually output the values. And the results are outputted as separate files, as shown here. And furthermore, when you're doing the live predictions, you can actually get the JSON back directly. So this is what it kind of looks like when it's raw. So in summary, when you're doing machine learning, you have training and prediction. And with what we saw today, we did our training on our local laptop, and we did prediction in the cloud. And the two are bridged with this exported saved model. This means that you have the flexibility to also reverse it, right? You could do the training in the cloud and deploy a model to a local machine or a local server. Say you have network considerations and latency. And of course, you can do both in the cloud. You can train in the cloud, output these data, and take your exported saved model and create a new prediction instance as well. So if you want to learn more about machine learning, more about TensorFlow, I've been putting on a show called AI Adventures on YouTube. You can catch it at the bit.ly link shown there, AI-Adventures. So I talk about TensorFlow. We recently did an interview with a Google Brain engineer. So it's really a lot of fun. So shameless plug there for that if you guys want to catch that on YouTube. And so finally, thank you guys for coming. And I've had some resources here I want to share with you, both the pages to Cloud Machine Learning Engine, TensorFlow, as well as the code examples that we looked at today. That second bit.ly link, wide and deep-code, links to a similar repository that I created, but with a different data set. So you can compare these two, and you can use that to help guide you when you want to load in your own data set to train on a wide and deep model. So thank you so much for joining me today. And we have Googlers waiting to hear from you and answer any of your questions. So fire away in our Q&A section.
So interesting. We're just getting our audiences back from the AI track, and they just finished learning about running TensorFlow in the cloud. So Jay, that's your favorite topic. And
it is definitely, look, and Yufeng Guo, who did that session. He's fantastic. He mentioned this at the end of his session, but I definitely recommend that you check out AI Adventures on YouTube, where he actually goes in depth about a number of different topics across AI. Also, TensorFlow itself is open source, so actually he was doing that training that you saw during that session on his laptop, right? And then he took that model and uploaded that to the cloud and did inference on the cloud to give you sort of that scaled capability. That said, TensorFlow also has things like TensorFlow Lite, which allows you to put those models onto mobile devices or even on IoT devices. So you can kind of reverse that model. So if you need that sort of more scaled training, you can do that too. And one of the things that Yufeng mentioned at the beginning of the session, and I just want to sort of reemphasize this, if you really want to move things back and forth between your training models, between your laptop and the cloud, or across distributed clusters, stick to those TF.estimators, because those really abstract things away. If you go too deep, you might over-customize and you might not be able to scale that training. So it's an important tip to remember.
Interesting. And I would really like to add here, the next session that we have coming up is how we can simplify the machine learning lifecycle, wherein we can explore data and have explained predictions and also deploy models in a simpler format. So that's our session that's coming up in the AI track. And so Jay, quickly, one more thing. You mentioned that about TensorFlow. So, if I can run it on my own laptop, then why do I need Google for?
Yeah, it really comes down to the amount of training they're doing. So if you've got a small data set and you just want to test things, you can test that on your local computer. But again, if I've got 1 million images that I want to train on, that's going to take my little laptop quite a bit of processing time in order to do that. So the idea is the machine learning engine allows you to scale that training and do that training much, much faster.
Of course, and that kind of computation power that Google can provide, that's really something I would not be able to do in my own laptop. That's true.
Great. So let's welcome back the big data track. So they were just talking about using open source technologies like Spark and Hadoop inside of Google Cloud Dataproc. The next session there is around the Internet of Things. So definitely a big data topic, and then one that is getting a lot of attention at the moment. So enjoy your session.
Welcome back to Cloud on Air, the journey from big data to AI. My name is Dinesh Kulkarni. I'm a product manager in Google Cloud team, and I'm going to cover how you can simplify the machine learning lifecycle, starting from data exploration all the way to deployment of models. We have Googlers waiting to hear from you and answer any questions that you have. So please fire away your questions in the Q&A section. There's a lot of hype around machine learning, but the reality is that there is real tangible business benefit beyond the hype. For example, out of the hundreds of use cases that we see inside Google, here are 4 that illustrates how machine learning is changing the world internally for us and externally for our users. For search, machine learning is the #1 improvement reason. You might have heard in the press how AlphaGo managed to beat the human Go champion using deep learning. That happened because of all the research that was happening in deep learning to figure out how to handle a game that's much more complicated than chess. Likewise, Google Photos is able to recognize objects. For example, in this case, it's able to figure out that it's a glacier. And that makes a big difference in terms of the consumer experience, being able to tag different images appropriately. But beyond these, there is tangible benefit that is happening behind the scenes as well. For example, using deep learning, we've been able to achieve 40% reduction in cooling costs for our data centers. Now, data centers are complex environments. Each one is different. It's in a different environment. And so there's no simple formula to figure out, or even complex formula, to figure out what's the optimal cooling required at a particular point in time. But there is lots and lots of data available about the temperature at different points, about the humidity, external temperature, server workload, and so on. Based on all this data, we were able to train deep neural nets to figure out the optimal way of cooling data centers and save a lot of money in the process. So your business too can use machine learning in a very straightforward fashion. One of the benefits of the machine learning research that was done in Google is a library called TensorFlow. It's an open source library that operates on tensors and is able to express a wide range of machine learning algorithms. Google Cloud Machine Learning Engine, the machine learning engine or ML engine, is a product that is a hosted version of TensorFlow that can be run at scale. So we can bring thousands of machines to bear and GPUs and soon TPUs to solve your problem. There are already companies that are benefiting from it. For example, Airbus was able to solve a problem that had eluded them for decades. They had lots of satellite images where they needed to remove the cloud cover to understand the rest of the image properly. Now, in a satellite image, snow and cloud look deceptively similar, and it's not easy to tell which one is which. But by using TensorFlow and machine learning engine at scale and doing the training using deep learning networks, they were able to solve that problem in a way that human analysts just could not scale up to. Likewise, AXA was able to improve their ability to assess risk by using prediction based on structured data. There are many such examples where there is tangible business benefit to be had fairly easily by using advanced algorithms, by using machine learning at scale. But advanced algorithms is not all about machine learning. There's a lot more to machine learning. In fact, most of the effort goes into the overall life cycle of machine learning. Because a data scientist can use an off-the-shelf or an available algorithm easily, they don't have to worry about it as much. But they do have to worry about collecting enough data, understanding that data by exploring it, to figure out if there's cleaning needed or preparation needed, to join data from multiple sources. And then once they have the right data, doing feature engineering to figure out what is the most likely predictor. For example, for data center cooling, it was understanding the temperature at different locations and the server workload. It could be very different for your business. But there is a lot of effort that is involved specific to your business domain in understanding and working with data. Model development is another significant activity where you take the features that you have, the data that you have, train a model, then evaluate the model to understand if it meets your needs or not, and then understand why it's predicting the results that it is, so that you're sure that it's doing the right thing, even beyond the test data or evaluation data that you're using to understand the model. Then even after these two steps, once you have a good model that you like, there is a significant effort involved in operationalizing that model. You need to be able to deploy it for prediction, have an endpoint that can scale as your load goes up or down, and manage the model over its lifetime. So for example, when a new version is created, you want to make sure that that version is at least as good as the one that you have in production, and manage these models over time so you can understand how to improve them and get more benefits. So in order to really get the most out of machine